Hi, my name is Shani Wolfson, and this is my final project for computer systems where I designed a memory allocator. So my memory allocator design. My memory allocator is modeled after the buddy system. The buddy system is a memory allocation algorithm that divides memory into partitions to try to satisfy a memory request as suitably as possible. This system makes use of splitting memory into halves to try to give a best fit. The reason it's called buddy is because we split the box into two halves, or buddies, and then both buddies are, and when both buddies are not being allocated, we merge them back together. In my program, I kept track of all the blocks of memory by using a doubly linked list. I made two static lists to hold these blocks, a free list with all the blocks of memory that had not yet been allocated, and a used list which kept track of all the blocks that were allocated. In order to make sure everything split nicely, I made sure all the blocks of memory were in powers of 2. This caused a little internal fragmentation, but overall was very efficient. So just to give a little bit of visualization, so this would be our free list on the left, and every single index is a power of 2. So 2 to the 8 is 256. So if our original block of memory that's given to us is 256, and we want to allocate, say, a block of 32, we're going to have to keep splitting until we get down to 32. And as we split, we move the blocks down the index so we always know where the blocks are and how big they are. So the way I structured my blocks is that I have within my block another block that has a header of a next in previous pointer. So it's a doubly linked list, as you can see below. The head pointer in the free and used list will point here in order to connect the blocks to make a doubly linked list. And my malloc gives this address to the user to use to store data. And that way it was like very separate. I heard you ask other people like what was their aha moment. This was kind of my aha moment where I was like, oh, this is so great and totally makes things great. So that was my aha moment.
So you're using headers also. So you're overlaying the block on top of the memory that's being allocated, or allocating new memory for it?
I'm allocating, I think, new memory for it. Like yeah. Memory manager state. So I basically held my list inside my memory manager. So free and used are a list of pointers which point to the head of each doubly linked list. Star memory holds the pointer to the memory given to us by the user in the init function and its size and where it belongs to. It belongs on our free list, which is going to be considered the max power of 2, because that's how high our list is going to go. Int num free and int num used keep track of how many blocks are at the element on the list. I didn't really need these, but it just felt easier to just look and be like, okay, there are 2 blocks here instead of having to like count each one and traverse the doubly linked list. So that's how I did it. I mentioned that my free and used lists were static. So this I found really cool. I found this on Stack Overflow on a, just like depending on if your computer is like a 32-bit system or a 64-bit system, a pointer can point to 4 bytes, which is equal to 32 bits. And a 64-bit system, a pointer can point to 8 bytes or 64 bits. So just depending on that, I made my list depending on your computer, either 2 to the 32 or 2 to the 64. So that was just something I found that I thought was really cool.
Most systems these days are 64-bit. I don't know of any 32-bit systems, except maybe our phones. Our phones might be 32-bit. Not sure.
Yeah, okay, well, I was just researching like how big is like a memory address and everything like that. So it just came up and I was like, okay, so I'll make the option. Like, why not? It doesn't hurt.
It's so cool that you spend some time learning about this kind of stuff.
Yeah.
It's awesome.
Wikipedia, I think, was actually my biggest resource because they had a whole thing on the buddy system and it just really laid it out. And like once I understood that, it was just like implementing little things like pointers and stuff that really threw me off.
So that was your aha moment, right? Like you found some article on Wikipedia that explained all of this stuff, and then you were able to implement it then, right?
Yeah, I just got caught up on like the syntax and just like random little things that really like just like C is an annoying language and I had to figure it out. But like once I got my head around it, it worked out really well.
Yeah.
Okay, sorry, my computer just froze. Okay, so meminit. So the first thing I do in my meminit is I basically set everything in my state to 0. So that way it's like cleared and I don't have to worry about any previous times that it's been used or anything like that. And then I set my memory to the memory that's given to us and the mem size and everything. And then I find out what power of 2 our memory can hold. So let's say the user gave 1024, that's going to be a power of 10. So it's going to go to the 10th level. And then I'm going to split my initial memory. So I really broke down like bit shifting and everything because like I kind of also discovered this thing and I was like, oh my God, this is so cool. And I want to like explain how I learned it and everything. It was great. And I was like, oh, this is great. We've been learning binary numbers. Like, I get this. So when you bit shift right every single time, you're basically just moving the 1 over, which is basically a power of 2. So when we bit shift 1024 until we get to 1, we're basically getting 10, which is great. So 2 to the 10 is 1024, which is the perfect size to go on our 10th level of our free list. But I also was thinking, okay, but what happens if someone enters something that's not a power of 2, like 1025? So we'd still take into account the fact that the max power is going to be 10. But then when I split my initial memory, so now that we have our memory and its size and what the biggest power of 2 is, we have to push it onto the list and push any remaining bytes onto the list as well. So back to our example, we have 1025, which is not a power of 2. We calculate the biggest power of 2 and then split it. So in our case, 1025, I would split 1024 in 1, and then the 1024 block will be pushed onto the list at level 10 and the 1 block at level 0. That was like an annoying problem I had, and I figured it out, and I was really happy about it.
Yeah.
And
So unfortunate that the world doesn't live in powers of 2, right? Like sometimes we have to deal with things that are not powers of 2, and we have to deal with it. But that's so cool. Like I vaguely remember somebody in the beginning of the class asked me, like, what possible use could there be for bit shifting operators? And I couldn't come up with an example. So next year when they ask me this question, I'm just going to point them to your final project. I'm like, this is why we have them.
Yes,
this is why they
saves
exist.
me so much time, because originally I tried just doing it manually and I had like this whole like calculation out, and then I was like, okay, there has to be a faster way. Like I always hear people talking about how they could do super fast calculations with like bit shifting. Like, I just have to like learn this and like understand it and implement it. And like once I got that, it like made things go so much faster.
Yeah, that's awesome.
Yeah, so this is kind of just like an example of how I figured out like what needed to be pushed. So I basically ANDed the mem size and the power of 2 size. So 1025 ANDed with 1024 is 1024, and then all these in between are all 0. And then when we get down to 1, when we AND it with 1025, it's going to be 1. So we just push that onto the 0th level. So that worked out like really well. Okay, push a new block. So this is kind of where our doubly linked lists come in. We set our previous pointer to null next to what the list header pointer is pointing to, which should be pointing to null if the list is empty, and to a block if it's not. We set the size to what it is on the free list. So if it's a block of 2 to the 3, it's on the 3rd level. And if our block next pointer is pointing to something other than null, aka there's already a block on the list, then we make our new block next pointer point to null, and we set the previous to our original block, and then we make our original block next pointer point to the new block and its previous null. Now you might not have caught all that, so don't worry, I have a visualization. So we have our free list and we have our header that's pointing to null. So if we want to add something, we're basically going to take whatever our header is pointing to and make our next pointer point to that. So original is pointing to null. Now our next pointer is pointing to null, and we make our previous pointer point to null. So there's nothing before it, but we're always keeping track of like what's in front of it and behind it and everything. So if we want to add something else, then again, we're going to look at what our header was pointing to. So our header was originally pointing to this gray block over here. And then we're going to have our next pointer still pointing to null over here on the right. And I just realized I didn't have like a laser pointer or anything. So I hope you're following what I'm saying.
I am. No worries.
Okay, great. And then our gray block.
I can see your cursor. Your cursor shows up, so it's all good.
Oh, okay, great. That's perfect. Okay. So then we're going to set our gray blocks previous to the new block, and we're going to set our new blocks to the original block and our previous to null. So that's kind of how we're adding things in. We're always adding things through the header. Okay, so my malloc. So when we first call my malloc, we have to input a size, and if that size is 0, we return null. Then we measure what size block we need by calling smallest block. So smallest block. So in smallest block, we take n, which is the size that was given to us in malloc, and we measure the size of our struct block and add it to the size of the memory we want to store. So once we know the total size of our block, we need to know where it goes on our free list. So we calculate what power of 2 is closest to our block size so we can store it on our free list. So again, I took advantage of like bit shifting here. I was like, this is just so great. I'm going to use this everywhere. So if we're given a size by the user and it's 25, then we're going to bit shift until we get to 4. So to the 4 is 16, which is not big enough to hold all of n. So I added this if statement afterwards, which basically says if like the power of 2 is still too small, we're going to like keep adding until it's bigger than n. So in this case, we would add 1, which is 2 to the 5th, which is 32, and 32 is big enough to hold 25. And this gives us a little internal fragmentation. We end up losing like 7 bytes of memory. But I personally, I think that was like a big dilemma I had while I was programming this, was whether or not to deal with like external fragmentation versus internal. And I realized it's just like not worth it to have the external fragmentation. I'd so much rather have internal. So that's kind of how my brain went regarding all of this.
One more thing for you to think about. While many of your test cases might have odd allocation amounts like 25 because you want to test your code.
Yeah.
I'm not sure in real life, like if you were to take a real application and measure the blocks that it's allocating, I think the majority of blocks are going to be like nicely rounded numbers because they're usually going to be structures that have like fields in them.
Yeah.
So they're probably all going to be like, you know, multiples of 8 because most fundamental like integers and floating points and doubles or whatever are going to be powers multiples of 8. So like I think in reality, the amount of memory that's actually allocated aligns nicely with the structure that you set up. It's just your test cases don't necessarily align. Does that make sense?
Yeah, I think so. I
So
think
like,
I just wanted to test for everything. Like I was just like, what
absolutely.
if this is like the case? Like, I don't know, like maybe there's a new structure one day. And that's
Yeah,
not.
no, you're totally right. Like you're absolutely in the right to test everything. But I just wish like the structure that you set up is actually fantastic because if I'm understanding the structure correctly, you can find blocks to allocate in logarithmic time rather than linear time.
Yeah.
And that's the point, right? Like you don't have to walk the entire list. You can jump really quickly to something that's already
Available.
close and
Yeah.
available. So that's awesome.
Yeah. Okay. So yeah, this would just add one more. So that way it could cover the 25 and now we'd have 32 and we have a little bit of internal fragmentation.
Yeah.
So back to my malloc. So now that we know how big our block is, we have to find a block of memory for it. So we go into our memory manager and we go into our num free list to see where there is some memory. So we know for our 32 block, we need to go to the 5th level of our free list. So we jump right there. And so in this while loop, if the 5th level is empty, we keep traversing up a level until we find some free memory. If we don't find any by the max power of 2 slot, we return null because there's no memory that's big enough to hold it. Let's say we don't have any memory at the 5th level, but we have it at the 6th level, which would be in chunks of 64. So we're going to call split free block, and we're going to keep calling it until we get a best free that is equal to our requested size block. And once we get that, we can allocate our memory. So split free block. So we're at the higher level where there is memory, and we're going to make a block pointer that points to this block we're popping off. We reset that block size to the level below it because we're going to split one level at a time. And then we make a second block by splitting our initial block into 2. The second block is going to point to the second half of the block's memory. And we calculate this by taking the memory's address of our original block, adding the new size, which is half the size of our original block, which we bit shift defined. So we know that the 2 blocks are right after one another in memory. Then we push both the blocks onto the level below it and on our free list. So just kind of a visualization of this. So we have our 64 and we're splitting it. So we know that 32 is going to start this 0 like address in memory. Obviously, it wouldn't be 0 in real life, but I thought that was so cool of Juliet's thing to have the relative thing. That was
Yeah, exactly.
like,
It's so easy to visualize, right?
I mean, I visualized it like that, but like that wasn't the numbers I was dealing with. So this so we would add 32 to find where the second block would start. So that's B. So we're still using addresses 0 to 64, but now there's just 2 blocks, which is great. So now pop a free block. So when we pop off a block, we're essentially doing the opposite of pushing a block onto the stack. We're just manipulating our pointers to connect the block. So we set a pointer to the block we're taking out. Then we set our header pointer to the next pointer of that block. If it's not null because there's another block, we set the blocks next in previous pointers to null. And then we decrement our free counter list. And then we return a block that we cut out. So again, just another visualization. So we're basically just taking our header pointer, pointing it to whatever this block was pointing to the next. Now it's pointing to this block. We set the next pointer of our original block of the popping block to null. And then we set our previous pointer to null because it's no longer pointing to anything else. And we get back to our starter position kind of. Which is great. Okay, so now we can finally allocate the memory. So we either got here because best free was equal to the requested power, which would make allocating O of 1, or we were going to have to split a bunch of blocks until we get one which is an appropriate size, which means in the worst case, we have to go through every level and split a block, which isn't like horrible, but like still. And just like in malloc, we're going to return a void pointer. What? Okay.
Yeah.
Just like in malloc, we return a void pointer to the block, and we're just going to move that block to our use list. So Allocating a block. So we make a pointer to the block that was just popped off the free list, and we move it to the used list the same way we push a new block onto the free list. If there is a block already there, we manipulate the pointers, update the num used list, and we return the block we just added to the used list. Okay, now we're ready to discuss free. Okay, so my free. Okay, so now we know how malloc works, how does free work. So as long as the user has given a memory input, we use the pointer that was returned to us in my malloc, and we subtract 1 so we can get to the block header.
Mm-hmm.
That was like magic for me.
Mm-hmm.
So the free block. So the same way we pop a block, we are going to pop a block from the used list by resetting all the pointers and cut out our block so that if there's another block on the list, the header is now pointing to that other block instead. We decrement our used list, and then we push the block onto the free list, and then we try to defragment any blocks on the free list. So defragmenting. So we enter in the level we are at in the free list, and we check to see if there are at least 2 blocks on that level. Then we make a pointer point to the header, and we check all the blocks and we try to merge them. If we can merge them, then we move up a level since there's a newly merged block there. And then we try to merge on that level. This is recursive until there's nothing left to merge.
Oh, wow. Okay. Wow,
Yeah.
That's really intense. That's excellent.
I know, because at first I was like, okay, I'll just call it if, and I kept like making all these if statements. I was like, wait, this is just recursive. I was like, is this going to keep going until it's done? So I was like, yeah, not a big fan of recursive functions. So I was like, okay, like this actually works really well.
Yeah.
So merge takes the header pointer of our list and whatever our traversal pointer is pointing to as its parameters. And it also returns true if the blocks can be successfully merged and false if not, to break the recursive function.
So you always try to merge. You try to merge into the biggest possible block you could and move it up the tree. You don't leave them where they are.
No, you always move them. Yeah.
That's cool. Yeah.
So our this is kind of just like our traversal thing. So it's looking at header and then it moves. Did I get rid of a slide? Oh, there was a second. Oh well. And it basically just moves to this next block. So it's pointing at this block and we enter in our header and our next block. So we try to merge. So we have our header pointer, which is pointing to the first block on our list, which we'll call A, and our traversal pointer, which is pointing to the next block on the list, which we're going to call B. So in memory, if our pointer to B is smaller than A, then we just want to swap them because we want to merge them in order. You don't really have to do this, but I just felt like it was better to do it this way. So once we have A and B in the right order, we want to see how far in bytes, how far in memory A is in bytes. If our memory starts at memory location 0 and A is a block of 32, we have no idea which block it is. So just to give you a visualization, so we have all these blocks of 32, A, B, C, and D. Just because we know it's a block of 32 doesn't mean we know where along our memory line it is. Mm-hmm. So once we know where A is, we want to see if A and B are on the same alignment as the size above them. So property line. So the idea behind this is that we want to see if our 2 blocks align with the boundaries on the level above. So we add 1, we calculate the size of the block on the level above. So 2 to the 6 is equal to 64. So if they align, I'm basically did like a module assessment here. So if they align, it'll amount to 0. So I realized that using 0 as my initial location as I was making this presentation was actually a bad idea because if anything you mod with 0 is just 0. So let's say we were trying to mod with 64. So 64 mod with 64 is equal to 0, 32. Anything else is going to have a remainder. So unless it mods to 0, then we know that they're properly aligned.
Yep.
So now that we know that A is aligned, we need to know if B is adjacent to A. So we take A's boundary and we add its size by bit shifting to see if it's equal to B. So that's basically just saying like we know that A is 32 and it's starting at 0. So we're going to add 32 to see if this 32 boundary is where B is. And if it is equal, then we know that they're aligned.
Yep.
So if they are properly aligned and adjacent, then we can remove A and B and push A onto the next level and adjust its size, and we return true so we can try to merge on that level. Otherwise, we return false in our earlier recursive function ends. So now we're going to remove the free blocks because now that we like have them up there, we don't need the ones below. So now that we know A and B can be merged, we just want to pop A and B off their list. So we reset the pointers for this level, and the header will point to null or to the next block if there is one. And we shift that block's pointers to be a starter block. And then we decrement our number free list. Okay, that's basically it. These I kind of used for my my testing. So memory set, I use this function for testing to basically reset state and mem init and everything. Mem max the max size allocation is the size given by the user minus the size of the block since it has to hold the size of the requested data. So example, let's say we have a chunk we're given is 1024 and our block is 24 bytes, and the biggest allocation we can possibly handle is 1000. Okay, performance analysis. So my memory manager implementation splits memory blocks in half until it can't anymore in order to allocate the smallest possible chunk it can. When freeing blocks, it attempts to merge them together into the largest possible chunk it can. These procedures of splitting and merging are the slowest. So best case performance. So my malloc is fastest when there is a block already available that fits the size of bytes requested. This is a constant time operation. My free is fastest when a block that is freed cannot be merged. This time is linear relative to the size of the free list the block is merging into. Worst case performance, my malloc is slowest when a very small block is requested, but only a very large block exists. This requires a large block to be split multiple times, which requires logarithmic time, like we said, relative to the difference in block sizes. My free is slowest when a very small block was allocated and a very large block was split many times to form it. This requires logarithmic time to merge blocks relative to the difference in block sizes, multiplied by the linear time for the size of the free list. And finally, our average case performance. My malloc typically requires a large number of block splittings to be performed at the first call, and then not many splits are typically required. And my free typically can only merge many blocks after all of the blocks have been freed. The last call is typically the slowest, and not many merges are typically required.
Yeah, so this is where like I was just thinking about how to measure average case performance. And average case performance is the one you really care about.
Yeah.
Especially when you're allocating memory, you expect the first one to take a while.
Yeah.
But you kind of don't care about the first one. You care about the average one. And in your particular case, right, like I imagine after a whole bunch of allocations, your memory allocator has already taken all your memory and you have a bunch of blocks at all the different sizes.
Yeah.
You're probably your average case performance, I'm going to guess, right? It's really hard to predict in advance, but I'm going to guess it's O of 1 for the average case, because the average case probably already has blocks that are
On every level.
on every level.
Yeah.
Right?
Yeah.
That's, you know, so this is where, like, you know, if you use this memory allocator and hooked it up to a real system and let it run for some time and then measured the distribution of all the blocks amongst, and that's how you would measure average case performance. It's really hard to predict in advance because it really depends on how the memory allocation is used. But like, this could be fantastic average case performance.
Yeah.
Where the worst and the best, or the best is 01, right?
Yeah, the best is 01 when it's exactly at that spot. And then, but average is also kind of like similar to that because it's usually like, I mean, yeah, average would be like if you had most of
it's
your
really hard
things
to reason,
yeah.
right? But I'm going to guess that average case like trends towards 01 over time.
Yeah, I didn't really think about it like that, but yeah, you're right.
I think so, right? Like, it's really hard to, you know, it's really hard to rationalize. But the more I think about it, like average case performance is going to trend towards 01. The more you use it, the better performance is going to get.
Yeah.
Right?
Yeah, yeah, you're right. Yeah.
That's awesome. That's like, I have to tell you, like, I'm blown away by the amount of work you put in to like optimize this thing in terms of performance for memory allocation, right?
Yeah,
And
I
the
don't
same thing for deallocation. It's the same thing, right?
Yeah, I don't know if you remember, but like I think like a month or two ago, like you mentioned in class, like, oh, by the way, our final project's gonna be a memory allocator. That is when I started, and I was like, okay, I'm gonna look this up and I'm gonna figure it out now before it's way too late. And I just like I've been like really like trying to like get it to like a really
Look, it really shows like this is the kind of stuff like, you know, you peel off the first layer of the onion and figure out the easiest way to implement a memory allocator. And, you know, you probably got there, like you just have a free list, you have a used list, everything is on the list. And then you kind of rationalize through that. But then you're like, you know, you can do better, right? Like, how do I do better? And how do I do better? And how do I do better? But like, you can only think about how to do better once you really understand how to do it to begin with, right?
Yeah.
Like you're not going to go from 0 to this model in one step.
No, this is like if I showed you what I was like first at, it didn't look like this at all.
Yeah, I'm completely blown away. Like I'm so incredibly impressed by all the analysis that you've done and all the thinking you've done around this. This is by far, I don't know if that's fair, and I know we're recording it, but this is by far the most thought out and optimal performance that I've seen. This is awesome.
Oh, thank you so much. I really appreciate you saying that. Yeah, a lot of hard work, a lot of tears, a lot of reading, a lot of YouTube videos also, like just like watching animations of everything. I'm a very visual person. So just like once I got it, I was like, okay, I can like run with this.
Yeah, for sure. YouTube is all of our friends, right?
Yes. I mentioned that to someone the other day in our class. I was like, you should like YouTube how this works. And they were like, I've never done that before. And I was like, how have you made it this far? Like I have used YouTube since day one to like just watch people explain like even very simple things.
Yes. Yeah,
Okay.
1000% agree with you.
I also answered your questions. So like, what did you learn? This assignment required me to become familiar with pointers and how to use them to manipulate data structures. My program made heavy use of doubly linked lists, which contained a lot of edge cases and pointer manipulation. The assignment also required me to think hard about the memory layout of my program and languages that manage memory for you, like Python or Java. You don't have to understand what the stack or the heap is to write useful programs. In order to avoid using heap allocation, I had to think in new ways to solve problems. For example, using static arrays to store the data for all the memory blocks instead of using like Python or Java lists. What was the most fun part? The most fun part of writing this was figuring out how the memory manager would work before I even wrote any of the code. When I started the assignment, I honestly had absolutely no idea how anyone would make this kind of program in the first place. And I was kind of just banging my head against the wall. And I knew that I would need to solve a lot of smaller problems in order to have like a working product. One of these problems I faced was figuring out how to manage data associated with each individual block. By reading about how other people have implemented their own memory managers, I learned about a trick where you can place data right before the address of a pointer. This way I could store data for my free function to use while anyone using my malloc doesn't see anything besides the raw pointer. I thought that was very cool.
Absolutely, yeah.
Yeah. The hardest part was definitely wrapping my head around pointers and pointer math. Before this assignment, pointers seemed incredibly mysterious and hard to understand. It was really hard to get doubly linked lists to work at first, and I had a lot of trouble visualizing what was going on in my code. But after spending enough time with these things, I'm definitely more comfortable with pointers.
That's awesome.
And yeah, that's it.
Two thoughts. First, I loved how you put all of your global data in one data structure called state.
Yeah.
That makes it so much cleaner. But I don't know if you realize this or not. It also allows your code to be what's called multi-entrant. Like if you need to manage multiple different memory pools,
Yeah.
your code is set up for that. You just use a different state structure. And all of a sudden your code can manage multiple different memory pools. You know, if that's what your system needs. Like you can imagine your system having, we kind of studied this in the beginning of the class. I don't know if you remember or not. Some memories are very fast and expensive, and some memories are slow and inexpensive.
Yeah.
And sometimes your program needs to differentiate. Like I need fast memory, I need slow memory. So you might set up separate memory allocators for fast memory versus slow memory, and then as your program asks for it, so your code is already set up for that, right? Like you can just set up a separate state structure for fast memory versus a state structure for slow memory, and then your program can just ask and you're good to go. That's really cool. It helps structure the code. And your code was also like really well formatted, really easy to read. And you know, I loved how you did all the bit arithmetic, you know, to optimize for block sizes, but also, you know, you found a creative use for bitwise arithmetic to figure out all this stuff instead of hard coding values. So that's kind of cool.
Yeah. Thank you. I didn't realize a thing about my memory like state manager or anything like that. I looked at a lot of other people's implementations, not necessarily of like the buddy system, but just like of other people, how they did it.
Yeah.
And I saw someone do that and I thought it was just like a really smart, clever way to do like just to like keep things organized. And I liked it, so I just implemented it. But I didn't think like much of it. So I'm glad you pointed that out to me.
Yeah, but I mean, like this is a classic programming pattern where like if you put all your state in something called state, then you can easily swap in a different state for it. Like you can have multiple different states. It's also what enables these cell phones to sleep, right? Because what all these programs do is if they centralize their state, you can take your state and store it in a database. And then your
Yeah.
program could be reinstantiated just by loading up that state and giving it to the program. The program doesn't know that, it went to sleep and woke up, right? That's how all of these modern systems deal with suspend, sleep, waking up. The programs just declare what all their state is, and that state is being managed by the operating system on behalf of the program. So like that programming style is really powerful.
Oh, it's so good to know. Okay, great. Now I'm gonna like relook at my code.
No,
Play around with it.
that was the first thing that I noticed, that you put everything inside of state. That was really cool.
Yeah, I mean, I just honestly saw someone else do it and thought it looked organized. Like I didn't really think much of it. So yeah, okay, that's so great. Yay.
That's how all of us learn, by looking at other people's code and like asking questions and realizing why they did it and incorporating that technique into our approaches. So that's
Yeah.
cool that you did that.
Okay, so on Ada, I can do my make tests. Oh wait, hold on, I have to. Plural, sorry. Hello. Oh, it's open. Okay. Oh my gosh, sorry. I've been having it open like manually, so like I didn't think about it. Okay, so these are all my test functions. I can show you the actual doc of what exactly I did. So I tried to allocate all the memory at once. I tried to allocate too much memory. I allocate 20 strings and then free them. I do too many allocations. Sorry, it's my dog.
No worries. All good. My two are upstairs. I'm surprised they haven't barked all night at all. So.
This is when I do too many allocations. So basically my malloc should just like fail out eventually because it's just too many. Allocate the same block over and over again. Also, it just like ends up not working out. Entering 0 into malloc, which is just like something that malloc does. And giving a null pointer to free, which should deal with it without crashing, and testing random sizes. So these were the things I tested for, and I used your stats thing to work. So so these are just the stats, and I formatted it nicely because I learned how to do that. So
yeah, that's cool. Show me what was the test runner that you used that printed out all the timestamps and stuff?
Oh, I used TimeVal.
Okay. Oh, so you set it up yourself to go measure the amount of time that each test actually used to run.
Yeah, I don't know. After Professor Broder's class, like he made us do it for all of our testing. So I just like got used to doing it. So it's like, okay, this is like part of testing, like is checking the time and everything.
That's awesome. That's really cool to see. So you figured out get time of day and all of that stuff in C on your own.
I watched a lot of YouTube. I don't want to say I did it on my own because it was like someone being like, okay, if you want to do this, it's like follow me step by step and we'll do it together. So I'm like, okay,
it's all good. Stack Overflow and YouTube. That's how any of us learn and get any of our stuff done these days.
Yeah.
And then you used printf with all the tab formatting and field length and all of this stuff to format your.
I think I did that, and so I did that over here.
Yeah.
Okay,
yeah, that's beautiful.
Thank you.
I am like totally blown away by all the work that you've done on this. It clearly shows that you spent an intense amount of time like really understanding this particular problem, and you took a lot of pride in your implementation also, like getting all the details done. Plus your presentation like was super detailed, covered everything. Like
was that okay? Really... I felt like it might have been too detailed. Like I noticed everyone else was like, okay, this is what this does, this is what this does, and I was like, oh, we don't have to go through it. Like
like this is why I leave it open-ended, so everybody can invest as much time or as they want into this, right?
Yeah.
I could tell you exactly what to do, but then your creativity and your passion doesn't show through. And I think in your particular case, like your creativity both in doing the project and the amount of pride that you put into your code really shows. Like really, really, really
shows.
Thank you so much. Congratulations to you for all the effort that you put into this project and all the effort you put into the presentation. It's fantastic.
Thank you so much. I really worked hard on this.
You can tell, like I can tell, and anybody who sees this video in the future can also tell how hard you put into this, how much effort you put into this, and how hard you worked on it. So thank you.
Thank you. Have a wonderful winter break.
You too. Take care.
Bye.